Kinematics Equation 2. Kinematics Equation 1 allows us to determine the velocity of an object based on its acceleration over time. We will now derive Kinematics Equation 2, which will allow us to determine the position of an object over time based on its initial position, initial velocity, and acceleration. The derivation on the next page combines equations using algebra. It's there to show you the connection of mathematics and physics. Your ability to recreate it won't be tested. You will use Kinematics Equation 2 extensively, so it will become very familiar. We'll start with the displacement equation from the last chapter, right here. Multiply both sides by 2, so you get 2 delta x is equal to v plus v0 times t. Then, substitute the first kinematics equation in for v. Okay, so we'll have v0 plus at plus v0, all within the same parentheses. Then we add the two v0s together, and we get 2 delta x is 2v0 plus at, all within parentheses, times t. Multiply through by t to get rid of the parentheses. And we have 2 delta x is 2v0t plus at squared. Now, let's divide everybody by 2. So the left-hand side turns into delta x. This 2 cancels, and you have v0t. And then finally, you have 1/2 at squared. Now, what is delta x? Delta x is x minus x0. So we replace that. And then to isolate x on the left side, we add x0 to both sides. So here we go. Here's kinematics equation number 2. Example 1. An object accelerates from rest with a constant acceleration of 2 meters per second squared. How far will it have moved after 9 seconds? We start with our givens. Since no starting point was specified, we are allowed to assume that x0 is equal to 0. And since you're at rest, we have v0 is equal to 0. So we have our acceleration here and our time. Here's kinematics equation number 2. And before we do anything, we get rid of the quantities that are equal to 0. So that's going to be x0 and v0. We're left with x is equal to 1/2 at squared. Substitute in the givens, and we get 81 meters. An object starts at rest and then travels 48 meters in 5.2 seconds with a constant acceleration. What is the magnitude of its acceleration? We start with our givens. And since we weren't giving a starting point, we'll go ahead and assume x0 is 0. Here we are at rest. Here's x, and here's time. We start with kinematics equation number 2. Before we start manipulating the equation using algebra, we get rid of any terms that are equal to 0. And that's what was done here. So now we have x equals 1/2 at squared. We need to solve for a because that's what we're looking for. Multiply both sides by 2. Divide both sides by t squared, and you have acceleration is 2x over t squared. Then, at the end, we substitute in our givens. Here's x, 48 meters. Here's t, and make sure you square it. Carry out the math, and we get 3.6 meters per second squared is the acceleration. Example 3. An object initially at rest is subject to an acceleration of 34 meters per second squared. How long, okay, we need to find time, will it take for that object to travel 3,400 meters? Let's write our givens, and let's see an object initially at rest, so that's v0 is 0 meters per second. We don't say if you started anywhere, so we'll just go ahead and assume you start at 0 meters. We have the distance we've traveled, 3,400 meters, and an acceleration of 34 meters per second squared. Looking at the variables, it makes sense to use kinematics equation 2. Because why? We're trying to find time here. So you can't use kinematics equation 3. There is no time in that one. And first, we're going to simplify this based on the givens. Before we solve for t, get rid of all variables that are 0. So that gets rid of x0 and v0t. We now have this equation, and we need to solve that for t. Multiply both sides by 2. You get 2x equals at squared. Divide both sides by a, and we're getting closer. We have t squared is 2x over a. Come on up here, we want t, not t squared. So we take the square root of both sides, square root of 2x over a, and finally at the very end, we substitute in our givens over here, carry out the math, and we get 14.1 seconds.